Hello, welcome to Mr. Ritchie's classroom for this film about empirical formula calculations. I'm going to try and keep it as short as we possibly can, but there are quite a lot of steps involved, so it might turn out a little bit longer than the 10 minutes, but we'll see how we go. Anyway, we're going to be using combustion data to find these formulae, and that's basically means to say that we're going to be burning things and seeing how much of the products we get. Okay, so hopefully by the end of the film you'll be able to use that combustion data, so this data that we get from burning things, to find the number of moles of carbon and hydrogen there are in a substance, to find the mass of oxygen that's in that compound using those moles of carbon and hydrogen, and then by the end of it to be able to turn all the figures that we've got together into an empirical formula. So let's see, here's a question which has come from the worksheet called Empirical Formula Calcs. Okay, and what the question tells us is that there are 4 elements in this substance, compound A. There's 5.2% of it is nitrogen, and the rest is carbon, hydrogen, and oxygen. They say we've burnt it. We've burnt 0.085 grams of it, in fact, so 5.2% of that is nitrogen, we're already told. And we've got to use these amounts of carbon dioxide and water to calculate the empirical formula of the substance. Now bear in mind that these numbers of moles of carbon dioxide are going to be related to the amounts of carbon and hydrogen present in the compound. Okay, why are we trying to find the number of moles? Well, let's just cast our mind back to what an empirical formula calculation looks like, and you might remember that quite often you end up having a kind of table that has your elements in it, whatever elements happen to be in it, but we know there's these 4 elements in this particular question, and the first thing you're told usually, if you're starting from simple things, is the percentage or the mass of each element. You can turn those into a number of moles because the number of moles is the mass divided by the molar mass, and then once you know the number of moles you can find the ratio, and you can plug that ratio into a formula, so you'll end up with a formula that has those 4 elements but also some numbers in it which are called X, Y, and Z because we don't know what they are yet. Okay, so that's where we're heading with this. Right, so bearing in mind what our question looked like, there it is, it's on the right hand side just so that we can keep it in mind. Okay, we're going to find the number of moles of carbon and hydrogen, and to do that we're going to use the number of moles of carbon dioxide and water, but we have to find the number of moles first. So let's just remember that the number of moles is given by the mass over the molar mass of a substance. So for carbon dioxide that's going to be 0.224 over 44.01. You can calculate the mass, the molar mass of carbon dioxide, right? And if you plug those numbers into a calculator like I have, you get 5.09 times 10 to the minus 3 moles. Okay, and you do the same thing for the water. So whenever you've got one of these combustion data problems, you're probably going to start off by doing this, and this was so remember 0.0372 grams of water, so 0.0372, and then this time we're going to divide it by the molar mass of water, which is 18.016, and that equals 2.06 times 10 to the minus 3 moles. Now why have we bothered to do that? Because that's told us the number of moles of carbon dioxide and of water, but not of carbon and hydrogen. Well, bear in mind that if carbon dioxide has 1 carbon atom in it, for every mole of carbon you have, you'll be able to make 1 mole of carbon dioxide. So the number of moles of carbon is always equal to the number of moles of carbon dioxide. Okay, and we've just found that here. Alright. How about the number of moles of hydrogen? Well, I need 2 moles of hydrogen to make 1 mole of water. So in other words, the number of moles of hydrogen is actually going to be twice as much as the number of moles of water that I formed. So it's going to be twice the number of moles of water. And these 2 formulas are worth remembering, okay, because they're used in an awful lot of combustion data problems. So if you want to save yourself thinking about why this works in the question, you'd rather just memorize a lot of a lot of recipes, which I don't think is the best way of doing it, but if that's the way that you work, then try and remember those two formulas. Okay, so anyway, I'm going to multiply this one here by 2, because I know that the number of moles of hydrogen is twice the number of moles of water, but I'm going to leave the one of carbon as it is there. So I multiply that by 2, find my number of moles of hydrogen, and that is 4.13 times 10 to the minus 3 moles. Okay, so I've got the number of moles of carbon and hydrogen there. Right. Let's move on to finding the mass of carbon and hydrogen. Well, you might be thinking at this stage, why would you want to do this? Because if you've got your table and you're saying, well, normally I go mass and then I find the number of moles. Well, I've just found the number of moles, so I'm going backwards if I do this, right? But bear in mind that although we're told the percentage of nitrogen, we don't know how much oxygen there is. So we're going to find the percentage of carbon and hydrogen, which we can do now because we know what mass of them there was in the compound. We know what percentage of nitrogen is. We can figure out the percentage of oxygen. Okay, so here we go. We're going to find the mass of carbon. Well, we just found that there were, so this is carbon here, we found that there were 5.09 times 10 to the minus 3 moles in the substance, and if we multiply that by its molar mass, because the mass is equal to the number of moles times the molar mass, then that is going to equal 5.09 times 10 to the minus 3 multiplied by 12.01, and that is equal to 0.0611 grams. Okay? We'll do the same thing for hydrogen. We decided, if you rewind, you'll be able to see how we got to it. We decided that there were 4.13 times 10 to the minus 3 moles. Okay, we're going to multiply that by the molar mass of hydrogen, which is 1.008, and that's going to tell us that we have 4.16 grams times 10 to the minus 3, sorry, 4.16 times 10 to the minus 3 grams of hydrogen in the substance. But bear in mind, these are both masses out of this. Okay, so we can also find the percentages of these two elements. So if we take 0.0611 and divide it by 0.085, that tells us that the percentage carbon is 71.9%. And we can do the same thing for the hydrogen, 4.16 times 10 to the minus 3, and divide that by 0.085, and that tells us that the percentage is 4.9%. So now we've got the percentages of those two elements. Right, let's move on. What can we use that for? Well, let's find the mass of oxygen, or the percentage of oxygen, using those things, because then we can find the moles of oxygen and we'll know the number of moles of everything, and we can carry on with our calculation. So here we are. We already know that we've got 71.9% carbon. We've got 4.9% hydrogen, and we've got 5.2% nitrogen. We didn't have to figure that out because the question told us it. So if we add those up, we've got a grand total of 82%. So that tells us that our oxygen must be 100 minus 82%, which equals 18%. Okay, so we now know the percentage of all four elements, and we can do the top row of our table, which is great because we're nearly there. We've nearly got the formula. Okay, so now we can go to our table, and we've got carbon, hydrogen, oxygen, and nitrogen. Okay, and we know the percentages, so I'll put the percentages in the top row. Okay, here we go. 71.9% for carbon, 4.9 for hydrogen, it was 18 for oxygen, and 5.2 nitrogen. Okay, it doesn't matter what order I do them in, but important that I know which one relates to which number. So now I'm going to go number of moles, because that equals little m over big M, but we can just use the percentage for the mass, imagining that there's 100 grams. So divide that by 12, and we get 5.99. Divide this one by 1.08, and we get 4.86. Divide this one by 16, and we get 1.125. So I'm just dividing by the atomic masses here. 5.2 divided by 14.01 for nitrogen, that's 0.37. And the last thing that remains to do here is to put the ratio in. Okay, and the ratio of these numbers is found by dividing them all by the smallest one. Divide that by 0.37, we get 16. Divide that by 0.37, we get 13. That one we get 3, and that's 1. So we can just go ahead and write our formula, CH, O and N, and we've got 16 of them, 13 of those, 3 of them, 1 of them we don't write ones. So there we are. There's our empirical formula. Okay, and that's about it. What would be a good idea now would be if you would watch the film that tells you how we can, once we've found one of these empirical formulae, how we can turn it into a molecular formula.